You've probably heard of shale, but what is it? Does it even exist? And why is it sometimes just a little bit controversial? Let's find out together and with this 1980s action movie training montage. Hi rock nerds, I'm the sentient bag of wet carbon known as Dr Brooke Johnson, and I'm a geologist that studies rocks that are billions of years old and the tiny wee fossils that we extract from those rocks.
If you're just wondering why I'm not in the lab, that's because I'm back home in the UK, staying with my family and visiting them for a wee while. I haven't been back for like 2 years.
This channel is where I talk about rocks and fossils and all the things that I think are cool in geology and the earth sciences. If you're into those things, then this is the place for you. The machine overlords request that you press the buttons and share the videos with your rock nerd pals. That would also make me really happy too, because I want to share the magic and wonder of rocks and fossils with everyone. There are also shirts, a tip jar and some affiliate links down below if you want to support the channel that way. And with all the admin done, let's crack on and look at some rocks. Shale is one of the more well-known rock types, and even people who aren't rock nerds like us have probably heard of it. The very first fossils I ever collected were actually from shale. Shout out to the Redcar Mudstone and the Yorkshire Lias. But what actually is shale? The standard definition of shale is usually something like a fine-grained fissile sedimentary rock. We talked about sedimentary grain size in the sandstone video, so go and check that one out after you've watched this one to learn all about that. In our classic classification scheme, there's a mouthful. Fine-grained refers to any grains that are silt-sized or smaller, and that includes things that you would commonly refer to as clay. So most rock called shale is some type of a mudstone, but this shale is made of sand-sized particles, so it's a sandstone. While this one is microcrystalline silica, making it a chert, and then this one is made of calcium carbonate, so it's a limestone. So how can that be? How can you have a shale that is also a sandstone or a chert or a limestone? Well, that's because shale is a texture and not a lithology. Lithology is the name given to the collected physical characteristics of a rock unit visible at the outcrop and hand specimen scale down to what you can see with a hand lens. So that's things including, but not limited to, colour, grain size and texture. So the lithology of this sample is mudstone. It's made of silt-sized grains suspended in a matrix of microscopic clay-sized grains. The clay-sized grains are composed mostly of minerals called phyllosilicates that form flat, platy crystals. When these crystals are compressed during burial and diagenesis, they lie flat like if you compressed a pack of playing cards. Diagenesis is the name given to all of the collected chemical and physical processes that occur when a sediment transforms from a soft surface sediment into an actual rock. Because the phyllosilicates lie flat and are generally quite soft minerals, then layers that are rich in phyllosilicates act as planes of weakness called cleavage planes, and that allows the rock to split into flat chips. And this is what gives shale its characteristic shaly texture. Flat phyllosilicate minerals are one of the most common causes of shaly textures in fine-grained sedimentary rocks, but they're not the only cause. In the sandstone example, some of the cleavage planes are caused by phyllosilicates, but some are caused by layers that have a size contrast with adjacent layers. So what do I mean by that? So that's like where layers rich in silt or clay-sized grains are next to layers rich in fine and medium sand grains. Cleavage planes can also form along layers that are rich in plant remains because the carbonaceous material is weaker than the surrounding mineral-rich sediment. So if you've ever seen coal in the wild or in an outcrop, then you'll know how crumbly and soft it is. Similarly, in the chert example, the cleavage planes form along organic-rich layers that were originally microbial mats growing on the seabed. The chert is formed from tightly interlocked microcrystals of quartz, which are much stronger than the thin, flat carbonaceous layers of the microbial mats. Finally, in the limestone, the cleavage planes formed along layers where the sediment was rich in platy carbonate aggregates. And that basically just means like little grains where lots of bits have clumped together and formed into flat chips before burial. These layers are also relatively enriched in platy iron-rich minerals and organic matter, and they're next to layers which are made almost entirely of microcrystalline carbonate. Like the chert, the microcrystalline carbonate formed on the sea floor and is made of layers of tightly interlocked crystals, so these layers are much stronger than the layers next to them that contain the platy carbonate aggregates, the iron minerals and the carbonaceous matter. So we would refer to these examples as being shaly, so you'd have a shaly sandstone, a shaly chert or a shaly limestone. When shaly layers are separated by much thicker non-shaly layers, we can refer to them as partings because that's where the rock breaks apart. So that's why shale doesn't really exist, because it's a texture of the rock, not a lithology or a specific rock type. But many people, including me, still use shale as a synonym for mudstone, especially if it breaks into flat chips. However, not all mudstone has a shaly texture, but that's something I'll talk about in a separate mudstone video, which I'm looking forward to because I like mudstones. Also, be aware that there are lots of old names for mudstone and shales that pop up in older literature, and some of these terms are still used in different parts of the world. For example, in parts of Europe, they use schist for any rock that splits into flat plains or chips. Now that includes shaly sedimentary rocks of all lithologies, but also metamorphic rocks like slate, phyllite and actual schist. So a good example of that is the schist scaton in France, which confused the hell out of me when I was an undergrad. It's actually a black shale, which we'll talk about later, not a schist. Shaly rocks may also be called argillites, which, along with the term argillicious, argillicious is an old term for mudstone or muddy sedimentary rocks. Where and how shales form depends on the type of rock that has the shaly texture. I'll discuss the formation of merely shudstones. Discuss the formation of shaly mudstones in a dedicated mudstone video. So looking forward to that. Mudstones. However, generally speaking, shaly rocks tend to form in environments where there's a mechanism that allows the accumulation of fine-grained sedimentary material. Now, most commonly, this is deep water, low energy settings such as large deep lakes or marine shelves below the actions of the waves or out in the deep marine basins. In these settings, large grains have usually been deposited in shallow water closer to the shore. Shaly rocks can also form in shallow water and terrestrial settings where the energy level of the depositional setting varies in time, so that there are periods where fine-grained material can accumulate in between periods of higher energy where it might get eroded. So for example, the sandstone I showed you earlier is from a river floodplain where active channels shifted periodically, allowing the buildup of fine-grained material which was held in place by plant roots so that it couldn't be eroded later when the river channel shifted back across. It just got buried by coarser-grained sandstones. Similarly, the carbonate example was deposited in a lagoon environment on a coast where the lagoon was protected from the coastal wave energy by reef complexes between the lagoon and the sea. Something to remember in all of these cases is that phyllosilicate minerals are not just produced as detrital grains from the erosion of existing rocks. In many deep sea and lake settings, as well as some special shallow water environments, like where ironstones are deposited, go and see the ironstone video after you've watched this one, phyllosilicates can precipitate from the water as a chemical sediment in pretty much the same way that chert and carbonates do as well. For example, the green and grey clay-rich bands in this iron formation formed from the precipitation of iron-rich clays on the deep sea floor over 3 billion years ago. As we've just seen, mudstone, including the shaly types, often forms in places where they can accumulate organic matter. It's no surprise then that many locations with exceptional fossil preservation, known as conservat Lagerstätte, it's a fun word to say, are hosted in mudstones and shales. The most famous of these is probably the mid-Cambrian Burgess Shale, which preserves the soft tissue of animals living on the sea floor over 500 million years ago. It's not just animals and plants that get preserved though. These microfossils were extracted by me from a shale that's over 1 billion years old. They're so well preserved that they actually retain nanoscopic features, but that's something I'm going to have to talk about another time. It's not fully understood why shaly mudstones preserve fossil details so well, especially with soft tissue, but current research, including by me, shows that it's a pretty complex web of interacting processes that happen to produce this exceptional preservation. The other kind of organic matter that shaly mudstones are good at preserving is the kind that generates hydrocarbons like oil and gas. This example of a shaly mudstone is very organic rich. In fact, over 12% of its weight is organic matter. To put that into perspective, any rock with over 1% total organic carbon is considered good for hydrocarbon exploration. We call mudstones like these black shales for obvious reasons. You can actually smell the organics in this one. It's kind of like a mixture of petrol and sulphur. This black shale is actually quite special. It's over 1 billion years old and is the oldest oil in the world. It's from the Roper group in northern Australia, and it's one of the rocks I've been dissolving to look at for little fossils in, like the little fossil I showed you earlier. Normally hydrocarbons are generated in a source rock like a black shale, and then later on as they mature they migrate out and become stored in a reservoir rock like a sandstone. and we call this a conventional hydrocarbon system. But over the last few decades there's been increasing attention on so-called unconventional hydrocarbon systems. And these are hydrocarbon systems where the oil and gas is generated in the source rock and then remains there, so the source rock is also the reservoir rock. These hydrocarbons are difficult to extract using regular methods because the source rock is compacted and such that the pore space is very tightly closed or restricted. And that means it's really difficult to get the hydrocarbons to flow and extract them. In these cases, hydraulic fracturing, also known as fracking, is used instead. In this method, small explosives similar to shotgun shells are detonated at the end of the well, and this fractures the rock. Then a fluid is pumped in and then extracted along with the hydrocarbons. Shales are ideal for fracking because not only do they contain a lot of organic matter and are therefore source rocks, but they're also very fissile, which means they're already highly fractured. And that's why shales have been so controversial in recent years. Despite the ongoing issues of climate change caused by the burning of fossil fuels, hydrocarbon exploration is continuing, and unconventional systems such as shale-hosted hydrocarbons are a key target. In addition to the climate-related problems, when not properly executed, fracking can cause other environmental issues, such as contamination of groundwater with waste fluids. If you've been out and about looking for rocks, then you've probably already seen shales, even if you don't know it. They could be anywhere. Shaly mudstones are most common in ancient marine and lake basins where they can cover really large areas. For example, the Precambrian shale I studied for my PhD has a thickness of between 200 and 1,000 metres, and it covers an area of tens of thousands of square kilometres. Pretty big, but nowhere near the biggest. The problem is that shaly rocks tend to be quite soft, and so they're easy to physically and chemically weather, especially the ones that contain lots of organic matter and pyrite. So the best places to find them are usually on coasts or in upland areas with cliffs. Fresh road cuttings are also another potential good place to look. Obviously be really careful in all of these locations and take the correct safety precautions, don't take any chances. There are also lots of resources online so that you can check out the geology of what area you're looking in to make sure that you're in the right place to find the shales, because it's no good wandering off looking for shales if you're in on the top of Cairngorm in the Cairngorms in Scotland, because it's all granite. Although there are some nice schists around Cairngorm, just not on the top. Because shale is so crumbly, shale cliffs tend to be quite unstable. One of the reasons for that is that some phyllosilicate minerals expand when they get wet and then shrink down again when they dry out. Montmorillonite and other smectites exhibit this behaviour, and that's why we use them for industrial applications like cat litter and anti-aging makeup. If you've ever used bentonite face scrub or volcanic clay face scrubs as they often call them, that's basically just montmorillonite. Shale can also be quite sharp, and it only takes a small bit falling from a relatively low height to give you a serious injury or even kill you. I've seen many people badly hurt over the years when looking for rocks and fossils around shale cliffs, usually because they thought they were safe because those cliffs were very close by to towns. This instability means that the areas around shale cliffs tend to be littered with bits of rock and often the fossils that they contain, so it's relatively easy to be a safe distance from the cliff and be able to look at and inspect bits of the material. And that's why it's often best to go with guided groups and tours, like from the local geological societies or other specialists. So there you go, a quick introduction to shale, what it means, how it forms, how the term is applied. Don't worry too much about this terminology though. People will usually know what you mean, whether you're saying shale or mudstone. It'll give them the general idea of what you're talking about. And it's not like the geopolice are going to pop up and give you a ticket. So, have you seen any cool shales recently? Let me know in the comments below. And while you're there, push the buttons for the machine overlords and check out the links. Until next time, take care, stay safe, latest potatoes. Just the bus going past. The boo. Shaly, I'm joking, don't call me Shaly. The carbonate example, similarly, 3 billion of your foolish Earth years.